This is my medium ISP, the LiDAR measurement device. It is able to measure distances between two objects that it is able to point at using servos and a TF Mini LiDAR sensor. Since there's a lot to demonstrate and talk about, the video is easily going to be over 6 minutes long, but I'll attempt to keep it as short as possible. As my first example, I have a processing sketch open which controls these servos over Bluetooth using the WASD keys. Here the text is showing its current distance between the object it is pointing at and itself, the object's signal strength, and the current yaw and pitch angles of the servos. On the right is the point list where clicking on one saves the position of the servos and the distance between, and if there is already a saved point, clicking on it again will overwrite it. This list allows you to save positions of different objects you want to measure. On the bottom is where the distance between 2 points can be calculated by selecting the text here and clicking on different points in the points list to switch out different points and to get a reading of the different distances between them. You can also select the current position of the device to measure from a fixed point to its current position. As you can see, as I move it around, the distance between changes because it is pointing at different objects around the room. If you ever forget where you saved a certain point, hover over the point in the points list you want to know and click space. The device will then move its current position to the saved point. As a proper demonstration, the device is going to measure the length of my hardware kit. First, I save the position at the bottom right, then move the servos to point at the bottom left, and click point 2 to save that position. I then configure the distance calculator to measure between point 1 and 2, and as you can see from measuring between the 2 points and comparing that measurement to real life, the device is pretty accurate, albeit with some deviation, as the LiDAR sensor and motors aren't the best out there. For another example, the device will measure the distance between the top of this cardboard box to the bottom of another. I set point 3 to the top, then move the servos to point at the bottom and set that as point 4. And again, comparing the measured distance to the one in real life shows its decent accuracy. If I close the sketch, the Bluetooth connection gets severed and the device switches to manual control. Here I can move the yaw of the servo using the rotor encoder, while the 2 touch buttons alter the pitch angle. The current information, like the one presented in the processing sketch, is then displayed on the OLED screen instead. To do distance measurements between 2 objects, I press the rotor encoder button to save that object's position. Then moving the device around calculates the distance from the saved position to the current one. Here I save the position which point at the bottom of my hardware box and move the servo up to the point at the top of my hardware box to measure its height. So to control the device with Bluetooth again, I reset it and open up the processing sketch to connect. Instead of the same processing sketch shown before, I will open up a second one. This second processing sketch controls the servos to scan the room and plots out the objects it scans into 3D space, creating a 3D projection of the room called a point cloud. As you can tell, there's a lot of customization to this sketch where most of it is done on the keyboard. Here I am setting the domain and range of the scan. I click R to reset the device to the beginning of the scan range. Hitting the spacebar will start the scan and a big red line tells the user where the LiDAR sensor is pointing at. While scanning, I can adjust the scan speed, control whether the plotting of points and the display of points is on. I can also control the state of the orientation axes, scan boundaries, and GUI. If I wanted a closer look at the scan, I could freely move around and zoom in with the mouse as well as rotate with the arrow keys. In the top left corner, like in the other processing sketch, is the current distance between the object it is pointing at, the object's signal strength, and the current yaw and pitch angles of the servos. Clicking space again pauses the scan, and here I can move the servos using the WASD keys. I am now going to set up a proper scan of the room to show off some of the other features. I click X to remove the points, then set the boundaries, click R, then start the scan. Here we can see that the scan is done as the servo has reset to its minimum position. And now that I have a visual representation of the room, I can measure between objects using the number keys by moving the servos. Clicking 1 for example selects point 1 and moving the servo around draws a color-coded line from the saved point to wherever it is pointed at. Clicking 1 again sets the line in place and as you can see it displays the distance of the line. This works for other points as well. By pressing M, the scan will change modes. The distance scan creates a color gradient of the different distances, with red as the closest and blue as the farthest. Clicking M again changes it to a gradient of signal strength colors, where green is great signal strength and red is poor. This signal strength from the LiDAR sensor is basically how reflective an object is. The more reflective, the greater the strength. Here I can adjust the distance color gradient, however, another scan needs to be done in order for the change to take place. I can also adjust the maximum distance of points shown, which improves the performance of the sketch if there are too many points on display. And that's about it for this project's long list of functions. Now I'll quickly run through the major parts that make up this project. The LiDAR sensor sends out an infrared beam, records the time it takes for it to bounce back, and uses that to calculate the distance. Therefore, surfaces need to be reflective for the signal to bounce back, which is why there is a signal strength factor. This distance result, along with the yaw and pitch angles of the motors that have pointed at two objects, are recorded by the Arduino-compatible ESP32 and sent over to the computer through Bluetooth. Here, the law of cosines calculates the distance between the objects using the distances and angle between the 2 points, which is calculated using this formula derived from the original angle between two vectors equation. Moving on, I had the PCB of this project designed in Eagle, the most notable feature being the cutout for the motor to fit in between and the thick traces for more current flow to the motors. With it, I also designed a case in Fusion 360 for the servos and PCB, which were then generously printed by my friend Liam Casano. Here it's got my name, the device name, and the law of cosines formula as well as the angle formula. One thing to note is that this angle formula was the one I used earlier on, but later realized was incorrect and had to subsequently figure out a new formula, which is the one I showed earlier. Now, before the end of this already long video, I'll show off a variety of scans at different locations around my house, and say a few last comments. Overall, this was a very fun but hard project. I really enjoyed figuring out the mathematics behind it, and then using it in a practical situation. Coding the processing sketches was time-consuming, but the payoff of seeing it map out a room for the first time was definitely worth it. Hopefully I'll make a version 2 with better components sometime, if I can one day afford the several $100 LiDAR sensors out there. Anyway, thanks for watching.